Good morning, everyone. My name is Erez Katz, and thank you all for joining us. Before we get into the subject matter, I wanted to provide some background. Lucena Research is a leader in computational finance and machine learning technology. We connect leading data providers with buy-side investment professionals, and we help them extract actionable insight from big data. I'm the CEO of Lucena, and I'm really excited to present how we are at Lucena apply deep neural network technology to investment decision making. Because I'm not a scientist, but rather a technologist, my goal today is to share with you the tactical aspects of essentially converting the deep learning technology to investment decision making in the real world. I want you to know that I'm very excited, and it's very important to us at Lucena to expose as many people as possible to deep learning, since I truly believe that in just a few short years, this technology will be essential to staying relevant, and especially in the wealth management business. My goal today is that at the end of this webinar, you will view deep learning neural networks as reasonably easy to understand and realize the enormous transformational potential it holds and how incredibly lucky we are to live in such an era of technological marvels. A few logistical points before we get into the subject matter. This is a 35 minutes or so presentation. We will leave about 10 minutes at the end for Q&A, but feel free throughout the presentation to post questions on the panel. Catherine and the Lucena team will be here and do our best to filter through some of the questions and respond to them either interactively during the webinar or at the end at the Q&A session. Okay. So this is a simplified version of a deep learning model. As you can see, it builds on multiple layers of neurons, and each neuron is connected to all the other neurons in its respective subsequent layer, and all the way down to the output layer in which a decision is normally made. In this case, we are classifying images of cats and dogs. Now, similar to how humans learn, there are three main ingredients to learning. The first one is we start with an uneducated random guess selection, and then we measure how far we are from a desired outcome. And finally, we apply corrective measures to get us as close as possible to the desired outcome. And then we try again. So it's an iterative process. So it's quite amazing to see how our brains are able to classify images with such ease. Even babies can classify a picture of a cat or a dog with just a few observations. But in contrast, a deep learning network could be quite involved, even for a simple task as distinguishing between a picture of a cat or a dog. You see, the idea of learning is to generalize the features or the characteristics of an object so that it can be recognized or classified with a new set of unseen data. In other words, we don't need to store every possible image of a cat to classify cats, but rather the machine needs to learn how to generalize or learn about the features that distinguishes a cat from a dog and apply that knowledge to future image classifications. So in order to understand how deep learning network learns, let's take a simple case of the hello world of deep neural nets, a handwriting recognition. If you take a simple handwritten digit and ask the network to classify which one it is, a fully connected network similar to what you see on the screen would come about. And here's how it works. It takes a small image of, let's say, 28 by 28 pixel, and it sequences all the pixels to an array of neurons, or a string, or a line. This is a one-dimensional input of all the pixels in an image. Now, each neuron is actually represented by a number, let's say 0 to 100 as an example, which accounts for the intensity of the color or the scale of the respective pixel. So in turn, the machine learns how to apply some sort of a multiplier or coefficient for each neuron as to determine how important that neuron is to the final classification or determination of what the image is all about. Now, each layer aggregates a set of votes based on the intensity of the pixels and their coefficient, and the subsequent layer then it kind of repeats the same process all the way down to the output layer in which the final classification is made. So in theory, imagine how the first layer detects edges, the second layer detects some sort of a partial shape, and subsequently the final layer is looking for the ultimate, putting it all together and determining full patterns of the selected digit. Now, just to summarize, a fully connected deep learning network traverses forward by passing votes from one layer to the other. But how does the network really learn? So the network learns by which, upon its final classification, we can assess how far the votes were from the labeled outcome. Labeled outcome really stands for what's the expected outcome. So we know it's a cat, so we expect the cat to be the outcome, and if we're off, how far the votes are off. And the process called backpropagation traverses backwards and adjusts the weights of all the layers one at a time so that the network gets closer to the desired score or the desired outcome. So you can see on the second image on the right side, you can see how the backpropagation is actually manifested by adjusting each layer in turns and dialing the weights of the neurons either up or down accordingly. Pretty cool stuff, huh? So by the way, these animations, the images are sourced from 3 Blue, 1 Brown, who publishes wonderful educational videos on YouTube, highly recommended. Some of the other images in this presentation are credited to the source below each image. But also I'd like to commend JJ Zhao, our super duper graphic designer who has helped some of the most amazing illustration in this presentation. Okay, so let's carry on. So how does the system really learn? How does it know how to adjust the weights either up or down? What's the system behind it? Well, it turns out that the distance between the model's vote and the desired vote can be expressed through a simple cost function, also called the error function. Using rather simple math, mainly linear algebra, maybe together with some calculus for partial derivatives, we can determine the model's current position within a slope of the error or cost function. So think about a graph that represents a function, and you're trying to travel to the lowest possible point within the graph representation. So subsequently, we can algorithmically change the weights of the neurons to travel forward or backwards in order to get closer to a local minimum of the cost function. So this process is called gradient descent, which is in essence the process of searching for the lowest point in a graph that represents the local minimum of the cost function. Okay, so now that we know a little bit more about how fully connected layers work, let's understand the concept behind convolutional neural networks, or CNN. So convolutional network is an extension of a traditional fully connected deep neural network by which we are adding additional layers ahead of the fully connected network. If you can imagine, in real life, images can get much bigger than 28 by 28 pixels. In addition, images have colors and have depth, adding more dimensions to the data, and it can get quite large. The convolutional layers precede the fully connected layer by which it extracts spatial information that's most meaningful to be used by the ultimate classifier, which is the fully connected layer. So the term convolutional is derived from the verb to convolve, which is to process or combine or to merge or transform information. In other words, the system learns how to create filters or kernels that extracts receptive fields or spatial information or patterns from the original image, allowing the systematic or mathematical representation of only the important pieces within an image so it can be classified effectively. The system kind of, in essence, creates filters that travels, step by step through step by step throughout the image and convolve the respective information mathematically into a simpler image representation. So how does a system know how to make these filters and what they're made of and how to create them? Well, it learns very much the same as the fully connected layers learn through backpropagation and error minimization. There are different cost functions that are considered as best practices for different situations, different type of networks. You would hear often people mention the term mean square error or cross entropy. But regardless, the learning process is actually very, very similar. Okay, so in real life, the structure of an image is much larger and more involved than so far we have depicted. So, adding the third dimension is really an important piece that we need to account for, whether it's a depth or RGB for red, green, and blue colors with a rich image as you see here on the screen. So channels are convolutional neural network components that are defined with the sole purpose of breaking down an image, a complex image, into multiple formats stacked above each other. The idea is to allow each channel to be convolved independently and ultimately merged or flattened before being fed into the fully connected layer. So what you see here, for example, is a nice color image of a bird and how it's broken down to three different channels. And again, they all traverse through the kernel, the filtering, the feature map. There is other types of conversion of downsizing the image sampling all the way down to the flattening before it gets to the fully connected layer. So we've seen the concept of computer vision enjoy great success in the real world so far, in a high degree of accuracy, from unlocking your iPhones with your face or tagging your name on Facebook, or even more recently with the autonomous vehicles. The question that should be asked is, can we build on the commercial success of image classification, or CNN, and apply the same concept to predicting stock prices? So more specifically, can we visually represent the state of a stock that would lead to a high probability expectancy of a price move? So in theory, we can very much, along the same concept of multi-channel images, define the state of a stock through multiple factor representation or multiple images. So each one represents a time series value of a factor that describes the patterns or the state of the stock over time. For example, a P ratio, how it's transformed over time, its volatility, how it changed over time, maybe beta transformation over time, maybe even social media sentiment analysis score over time. So as we at Lucena aggregate so many alternative data sources, we can describe each one of them individually as a time series of its own. So each indicator is represented by a time series trend, and each indicator is an image that can be treated as a channel inputted into a CNN, very much like we've seen in the previous image that we know has had success commercially even today. So we tried this, and we tried it many times and have not been successful. And we were scratching our head to see why we haven't been successful. And then we came up with an idea of maybe creating some sort of a richer image representation of the data, and came across an interesting approach called RP, or recurrent point. In this example, you can see a sine wave time series of 63 data points converted into a 63 by 63 rich image representation. Essentially what it does, it's a pretty simple math, takes the Euclidean difference or distance between every 2 points in the time series, and the shades of the cells are proportional to the distance between every 2 points. So we selected a sine wave because we wanted to see if the deep learning model can learn an obvious repetitive pattern. And good news, by only applying a simple logistic regression, which is a much simpler form of machine learning model, Voila, the machine was able to achieve an out of sample accuracy of 97.6%. You can see on the slide a backtest of a fictitious stock that behaves like a sine wave. What's important here to note is that the machine was able to identify and exploit the information in a sine wave after it was converted into a rich image. The takeaway for this exercise is that if there is information in the time series, whatever that time series is, the assumption is that there's a good chance that the machine will be able to extract it. So building upon that, it turns out we can just as easily migrate other time series sequences and trends to images. And here are just a few factors represented as 63-day time series history and then converted into a richer 63 by 63 images. Now, as a side note, I wanted to describe something. You can see here on the recurrent point, there is a symmetrical representation along the diagonal line here. So in essence, the same information repeats almost mirrored between one side and the other. Even though we do have what we call a 50% degradation of information efficiency, we still have a lot more information points than just 63 points, as you would see in the traditional chart of a pattern. So we actually have a 63 times 63 divided by 2, which is obviously a much richer information that can pass through the neural network than the actual time series image itself. And just as a side note, GADF, what you see on the bottom here, it stands for Gramian Angular Difference Field. That enables a much richer implementation by which we are really utilizing the entire spatial information here of the image of 63 by 63. These are 21 by 21, but just to give you the idea of there are other methods to convert time series images to richer representation. Okay, so what do we do with this? So imagine we have now a picture of a state of Apple using its 63 historical time series representation, but not just its price, but also its ranked, its beta rank, earnings call, rank, volatility, and other types of features, all stacked on top of each other to create some sort of a composite state that is an image. It's a complex image that shows how does Apple stand today, and is that picture strong enough to give us the ability to identify over time in history that when these stars all fully align exactly together, they created the condition by which a buy signal is most probable. And that's kind of how the machine learns. It basically, we feed in to the system lots of images just like that every day for Apple, and we tell it during the time that we train the machine which combination of images yielded an up move of the price and which did not. And the machine starts to generalize what situations, what images, a complex image can actually be deterministic of a price move, whether it's going higher or lower. Now, before we put this whole thing to the test, we did one more thing that I want to mention. It's very important, which is the hyperparameter searching. So our friends at Google Brain created an amazing and a robust set of libraries and software development framework that enables even a novice Python developer to execute deep learning code. So the real challenge, however, is how you configure these pre-existing code libraries to maximize efficiency. Realistically, there are many dials and knobs to turn, and doing so by hand will only lead to great frustration and disappointment. I can tell you from experience that CNN and in general deep learning technology can cause a great deal of frustration, as many times the AI and deep learning engine is unable to learn. One way to identify the best configuration is to conduct a hyperparameter search. It is a brute force sort of a grid search of many permutations that are set to identify the most suitable parameters for the machine to learn and predict. This is not the actual model that's learning. It's the framework of the model before it starts to learn. So only after we've identified the structure of the model and how it should learn, then we train the model on some new data and ultimately test it on an and validate it against a completely yet another set of new data, and ultimately test it in real life on a roll forward basis. So this diagram describes, in a way, our network that's being used actually in this exercise. And you can see we use 32 channels. We have a convolutional layer, a max pooling layer, a soft max, which is an activation function for a convolutional network, then a flattening layer, and you can see the input and the hidden layers, the output. And again, at the end, after all that, we get whether a buy or do nothing kind of signal. And on the right side, you can see in a table what our, again, hyperparameter search identified over the course of its search. These, by the way, searches can take days or even weeks sometimes. So this is kind of a very involved and computationally intensive process. Just to summarize, you can see that there are really three time frames that we break down historically our testing or training or our development kind of time space. There is the hyperparameter searching time frame. Once we found the winning framework, we applied that against a training base on historical data. And then we get the optimal model that was trained and tested against new input data to get a buy or a sell signal. Okay, I want to show you now the results of the of our research. So what you see here is a TensorBoard. TensorBoard is a wonderful platform that, again, our friends at Google Brain created to allow us to visualize the training in progress. As you can clearly see how our model gets better over time. So what you see here is basically epochs. Epochs are essentially a set of training data or set of data that gets trained over time. So we push new data and the system traverses back and forth to learn. It gets better over time. And you can see here as we train the system over time, the accuracy gets better and better. And it gets to 94.6%. This is, by the way, in sample. So that's not a real world example, but you can see how the system gets better over time. The same thing goes with the precision, how the system gets more precise in its true positive classification over time. And on the right side, you can see here how the loss function becomes effective, how we can reduce the cost over time from 165 to 0.42. Now, again, this is just to show you how the system learns to get better as it passes through training data, which basically says, look, here is the input, and here is what we expect the output to be. So we tell the system what we want it to be, so you can compare against what it actually found and minimize the cost function to get the loss to be as low as possible, and by which it increases the precision and the accuracy. Now, it's very interesting because, again, one of the things that we have within Google's TensorBoard framework is the ability to see in real time how those models, as they're getting trained, are tested against out-of-sample data. And you can see quite remarkably, this is not what you would typically see after many, many iterations. You can see here that out-of-sample on new data, as we were training the in-sample data, how the out-of-sample increases in accuracy over time as well, and how the precision gets better over time, and how we reduce the loss over time just as well. So it's quite nice to see that the same process that we saw in sample sort of repeats out of sample. And what's interesting also to see here that the precision that we see here after 140 epochs, which is a small number of epochs, sometimes you go after 10,000 epochs or even more to learn a complex system. But in this case, after 140 epochs, we got 69% precision. Now, to give some perspective, in a true trading paradigm, 53% is what we call best practice to overcome transaction costs and slippage. Getting 69 is extremely high, could be even at times unrealistic, but it's very, very encouraging for this specific exercise. By the way, you can see here, we also check to see how many times you have a vote to buy, because if you have a very robust time frame during the time Apple is going high all the time, yeah, it's very easy to get a good buying signals because you'll be right most of the time if you are betting on an uptrend while an uptrend actually occurs. You can see that we're getting actually 50% up or down votes after 140 epochs. So we are actually a 50% chance of being successful. And you can see out of those 50%, when we actually are betting on buy, we're getting 69% precision, which is very, very encouraging. So before we show you the backtest, I want to give you one more piece of information. So in order to make the selection dynamic that survives the test of time, we refrain from using what we call hard values. For example, we label the data dynamically by how the stock ranks relative to its peers versus its absolute value. So a P ratio of 12 or 14 is not as meaningful for us because it could be a very good number in one market regime and maybe not so good in others. We are measuring P ratio against its peers, how you rank today against your S&P 500 peers in Apple's case, and how that ranking transforms, moves up or down over time. The same thing goes for alpha, for other types of ranked features. So again, ranked features can survive any market regime because the relativity to your peers should stay constant if you are stronger than your peers or weaker. Now, at the same time, we apply dynamic label data using ATR. So again, if you think about how we train the models, we don't necessarily say, hey, tell me when Apple is going to go up by 1% or 2%, because that number is very dependent on the market volatility or Apple's specific volatility. What we did in turn here, we've applied what we call dynamic labeling, by which we use ATR. ATR stands for average true range, which measures the volatility of that stock during a period in the past. So we can see here, we say, look, I'm going to measure the ATR, and I'm going to always recommend to buy Apple if I expect the price to meet or touch the upper threshold of the ATR in the next 21 days. So essentially, I'm going to always recommend a buy if the expectations are that the future price is going to move high according to its recent volatility and touch the upper threshold before it touches the lower threshold. That's one way to create dynamic criteria for determining whether you should buy or sell the stock, as opposed to hardcore or hard-coded value of 1% or 2%. Just wanted to mention that. That's really important for us to help the machine learn and get better. What you see here is a backtest, and I'm almost done here. The results are exposure adjusted. What does it mean? It means that we only assume the relative return of our strategy when we are not sitting in cash. So if we are, for example, in a very long, protracted downturn, and we sit in cash, and Apple goes down 5%, it doesn't really mean that we are smarter than Apple. Maybe in some cases it is, but for this exercise, we're trying to evaluate the efficacy of the buy signal. So when we say buy, and we are in the stock, we actually fully invested in Apple, how does the return of our analysis compare to being in Apple all the time? So that's kind of what you see here. The same thing you can see here, by the way, we achieved a pretty impressive returns year over year during the in-sample, the in-sample time frame. And when we carry that knowledge out of sample on brand new data, the behavior continued to manifest itself. Even though it's a shorter time frame, it continues to behave very, very well. And again, people will ask me, why did you choose such a short time frame in the out of sample relative to the in sample? You know, again, best practice is to do what we call a 5-to-1, which means 20% of the time that you apply to the sampling and the training, you want to apply out of sample. But again, in general, you would be correct that we should really have a much longer backtest out of sample, as well as forward testing. But this is just for the purpose of this webinar. I wanted to kind of underscore that. Okay, that's all I have today. If you made it this far, congratulations. I'm going to open up the podium for some Q&A, and let's see kind of where we have some of you guys who may have some questions about the presentation. So Catherine, if you
Yeah,
have any
thank you.
questions.
Perfect. Yeah, we definitely received some great questions. I pulled out a couple that we can discuss. So Trevor asked, why have you chosen to use a CNN as opposed to an RNN with LSTM or GRU cells?
Yeah, it's a good question. So just for those who don't know what RNN is and what it provides. So LSTM or RNN, recurrent neural networks, essentially is the only network that I know that does not do what we call a feed forward type of neural knowledge transformation. It kind of goes back and forth, and it's got this method called LSTM, which is long short term memory, that allows you to really maintain information relevant to history. And the nice thing about LSTM that it knows how to consider what historical data is important to be kept or discarded. The answer to your question is it's a very good point. We actually do use LSTM, and we are actually evaluating LSTM in context of forecasting stock prices as well. So your point is well taken. We thought that the CNN application that we showcase here has some usefulness to it. RNNs are notoriously difficult to train and require a lot more computational power. Although your point is well taken, for time series forecasting, RNN is absolutely a suitable solution. Anybody from Lucena, if you, any of our quants, if anybody wants to add anything, feel free, but let's move on to the next question, Catherine.
Great, so Matt asked, must factor time series be in visual form, or can they be in tabular quantitative form with the completed model? Are you able to also get a table of relative factor importance?
Yeah, so I'm not quite clear on the question, but the question is, can you not use images essentially and feed those to the CNN? So we tried historically to feed time series data notionally into the network. So essentially you pass the p ratio of today, of yesterday, the day before yesterday, and all the way back 21 days or 63 days, 1 month, 3 months historically. And we tried hard, and we received I would say moderate results. We were trying to find something a little bit more interesting and exciting and richer, really, to see if we can really apply the same image classification that we see working so well in the real world to stock pricing.
Great. We have a lot coming in, so we'll get to as many as we can, and then definitely we can follow up after with additional questions and information. Dr. Costas asked, what kind of embedding do you use for the RPs, time delay and dimension?
Okay, this is over my head. I'm not sure I understand the question. So as far as time delay, just let me kind of explain how we capture our indicators. I hope this is answering your question. But again, if any of the quants wants to chime in, please do so. We capture information and data, time series data, on a day-by-day basis. So when we use data, we can only use it in the context of a future use. We can never apply future knowledge, backwards. So data is always, trained historically, but you cannot use trained data historically, only into the future. It's time series data. It's daily. We have some monthly data that's mostly macro information. We never go below that. We don't go to the intraday signals other than just stock prices and technical factors that are intraday. But most of our signals, also from alternative data providers that we work with, are daily signals. If anyone wants to add to my question, please, to my answer, please feel free to chime in. Good. I did a good job. So next question, Catherine.
Bryn asked, how much data is required to successfully build a model, and how long does the model function before requiring retraining?
That's an excellent question. So I want to start, and then we'll let others chime in as well. So um, the more data you have, the better. However, if you feed all the data at once to the network, you're going to lose its efficacy. So there is a process called feature selection. If you see the channels that I mentioned before, really, if you think about it, we can actually have 32 features kind of merge into 8 channels in one aspect or another. And really and truly, you can determine which features are more relevant together than others for a given situation. Now, the other question is how soon or how frequently do you have to retrain the model? That's a good question because we always struggle with that here at Lucena. Um, by the way, you can actually test the training frequency as part of the hyperparameter searching mechanism. But the nature of the model, as opposed to a static picture of a dog or a cat, is that it's non-stationary, right? The market changes all the time. Even when you identify a predictive signal, after a while, it's just a matter of time before somebody from Goldman or somebody from JP Morgan realize that there's a signal out there and boom, it's evaporated. So and by the way, no bad reflection on Goldman or JP. This is the nature of the market. But the important thing to remember here is that it's very important to retrain the model, and the retraining frequency again is determined by the hyperparameter search. But in general, it's good to retrain the model frequently in order to accommodate changes in market regime and changes in market conditions. So that's one of the things that allow us as technologists to sort of fight the dynamic nature of the market, is to retrain the model, associate new features, new data elements, and let the machine kind of identify, again, through trial and error, through error minimization, through a learning process, what works now on a roll forward basis.
Great, we'll jump to the next one. Todd from Battlefin asks, are you typically starting with the same convolutional layers on different stocks and then allow the machine learning to change over the training period so the end results and signals are different on each stock? Or does this stay more uniform regardless of which stock is being run through the system? Basically, how different do the models become as you continue to train on individual stock data?
Excellent question. Excellent question. So Todd, here is the consideration. It's really better to train the model on a given stock at a time. The challenge is sometimes you don't have enough data to train on a single constituent. So what you do is you try to find other similar constituents that has similar data that gives you more data to be trained on. Data is expensive. It's very hard to obtain and very hard to obtain good data and clean data. One of the things that we do obviously at Lucena is we aggregate alternative data, we validate them, we clean them, and then we apply them to our constituents list. And if we want to try and train effectively, the more data we have, the better. However, it needs to be data that has similar characteristics to the underlying constituents. If you train on independent or uncorrelated types of stocks, you're going to confuse the network and essentially fail to provide good results. Okay, Catherine, let's do 2 more questions and we'll take it from here.
Perfect. Drew asked, in the historical data, are you including news released about the company prior to the price rising or falling?
Yeah, so press release or news feed, absolutely. It's one of the data sources that should be considered heavily. There are great companies out there that apply what we call natural language processing. They provide the sentiment of a news article towards a stock. They can do it very quickly and very effectively. Again, that can be captured as a daily time series data or even intraday, and basically allow you to consider those signals as price moving actions. Again, normally we don't take only one data source at a time. As you saw here, we were combining multiple orthogonal independent data sources into one composite kind of signal that the machine is trying to exploit. One more and we'll close it today, Catherine.
So Brent had one more. He asked, are you manually creating features or do you have an automatic method to generate features, something like an attentional NN?
Yeah, that's a good question. So, when we process a new data source, obviously we don't source any of the data. All the data that we have comes from data partners that we work with, and we help them basically shine the alpha and the quality of the data. But one of the things that we do is we create additional features on top of their existing features to allow the machine to be more effective. I mentioned the ranking technology. We apply time decay on features that are not, published frequently enough. And we create additional features such as moving averages and other types of domains to allow us to measure, again, the transformation of values over time. So yeah, we definitely create new features. That's one of the things that we do. And we have a data science process and team that completely dedicate themselves to not just evaluating the efficacy of a data source, but enhancing it, making it better and more appropriate for distribution of derived signals or derived content for the buy side to enjoy and make a decision based on. Okay, I want to thank everyone for sticking around so long. We are almost 45 minutes into the presentation, and we have almost all the attendees still on board. I'll be very happy to respond to people. I'm sure Tucker, my co-founder, our PhD chief scientist, who is the brain behind many of the things that we do here, will be happy to get more scientific and more under the hood. For those of you who are interested, we will be following up with some additional webinars similar to this one. And I want to thank you for coming in and joining us and for listening in. And have a great day. And we'll talk to you soon.